All right. Hopefully you're having a good day and you're ready to learn some math. Today we're going to be trying to add, subtract, multiply, and divide rational expressions. And we should talk about what a rational expression is. When we're talking about algebra, we're talking about two polynomials written as a ratio, it's anything that can be written as a ratio of two polynomials. So we're going to involve dividing algebraic expressions. And because we're going to involve dividing, it's going to look a lot like fraction skills from middle school. We want to be able to deal with some common denominators, and we need to know about the reciprocal. And so the reciprocal of a fraction is, of course, when you flip it upside down. It's the same as dividing it by 1. So one divided by a fraction will give you the reciprocal of a fraction. All right, so unlike some of these other videos, we're going to start with a warm-up, and you're going to try to do 3 middle school problems on your own. 2/3 plus 5/7, 3/4 times 2/5, and 5/7 divided by 2/3. If you know how to do this, you can skip the explanations, and I'll do that for you automatically if you get them right. All right. In this first one, to add 2/3 plus 5/7, whenever we are adding or subtracting fractions, we need to have a common denominator. And we notice that 3 and 7 are not common denominators. And we have a trick, which is that we're allowed to multiply fractions by fancy forms of 1. And we're going to multiply by something in the denominators of both of them to get them to the same place. I can multiply 7 times 3 to get to 21, and I can multiply 3 times 7 to get to 21. Sometimes there will be smaller numbers you don't have to necessarily multiply by the other one, but we just want to get to a denominator that's the same. To keep this fraction actually the same, I can't just multiply by the denominator by 3. I need to multiply by 3 over 3, because 3 divided by 3 is 1, and that keeps the fraction having the same value because multiplying by 1 doesn't change anything. If I want to multiply the denominator by 7, I also need to multiply the numerator by 7, because then I'm multiplying by 1 and not changing the value of the fraction. When we multiply straight across. 7 halves, 7 times 2 is 14, 7 times 3 is 21, and 14 21st is 2/3, just written a different way. 5 times 3 is 15, 7 times 3 is 21, and 15 21st is still 5/7. But we now have a common denominator. And the rule is when we're adding or subtracting fractions, we leave the denominator alone, and we add or subtract the numerators. In this case, we're adding. 14 plus 15 is 29. I might want to check to see if this can be simplified, but in this case, it cannot be. And so our answer is 2/3 plus 5/7 is 29 21st. Okay. When we are multiplying, this is the easiest of all the operations we can do with fractions. We just multiply straight across. We multiply the numerators times the numerators and the denominators times the denominators. We do not have to have a common denominator. We don't here, and it doesn't matter. When we multiply, 3 times 2, we get 6. 4 times 5, we get 20. And we want to be careful to look for, is there any way to simplify? And yes, 6/20ths, the numerator and the denominator share a common factor of 2. And so we're going to divide by 2 over 2. This doesn't change the value of the fraction because 2 divided by 2 is 1, and dividing by 1 doesn't change the value of something. 6 divided by 2 is 3. 20 divided by 2 is 10, and so 3/10 is the simplified form of this multiplication, this product. All right, we want to find the quotient, which means to divide these. We're going to do 5/7 divided by 2/3, and hopefully we remember from middle school that when we divide two fractions, we leave the first fraction alone, and we multiply by the reciprocal of the second fraction. And now it's just a multiplying problem, just like we did right before. We multiply across. We do not need any common denominators. 5 times 3 is 15. 7 times 2 is 14. And we are done. 15 14ths is the quotient, which means the result of a division. Okay, let's see how we can apply that to our algebra situations. Here we have 2 rational expressions. They're the ratios of 2 polynomials, subtracting. And we're going to take the same idea as we did up here when we were adding fractions. We need a common denominator. And we're looking for something we can multiply the denominators of both of these to get to the same thing. And similar to how we did up here, where we multiplied this denominator by 3 and this denominator by 7, I am going to multiply this denominator by x plus 3 and this denominator by x. That way they both have a denominator of x times x plus 3. They'll both have a denominator of x times x plus 3, and they will have a common denominator. Just like up above, I need to multiply by the same thing on the top because x divided by 3, x plus 3 divided by x plus 3 is 1, and so I'm not changing the value of this. Here I need to multiply by x over x. And when I multiply the numerator, x times 2x, I get 2x squared. When I multiply the denominator, I'm going to leave this in factored form, x times x plus 3, although if I wanted to, I could distribute it and get x squared plus 3x. Here, 5 times x plus 3, we need to notice that 5 is multiplying times a binomial, and it will distribute. The 5 will multiply times the x, and the 5 will multiply times the 3. 5x plus 15. And the denominator is also x times x plus 3, and I'm going to leave it in factored form. Just like above, when we have a common denominator, we're going to leave the denominator the same, and we're going to combine the numerators. Now, this is the most tricky part here. I see students mess this up all the time. This subtraction is subtracting both this and this. It's kind of like the subtracting is distributing. So we have 2x squared minus 5x minus 15. Notice that both of these signs are minus signs because that minus subtracted both of these. If there had been any like terms, I would have combined them. But in this case, x squared, x, and constants are not like terms. And so this is my answer. This is my answer. If I really want to, I can multiply out the denominator. But a lot of times when we're dealing with rational expressions, we will just leave the denominator in factored form. It's oftentimes more useful. But this is right too. This is fine. Okay. Next, let's look at multiplying. And this looks crazy. This is a giant thing. X plus 4 divided by x squared minus 25 times x minus 5. And here's what we're going to do. We're going to do exactly like we did up here when we were multiplying. When we have fractions, we multiply straight across. And the same is true here. I'm going to multiply these across, but I'm not actually going to distribute and multiply out. I just mentioned it's often easier to leave it in factored form. And I'm going to leave this as x plus 4 times x minus 5 divided by x squared minus 25 times the other denominator, x squared plus 6x plus 8. And we're going to see a trick here that we're going to use a lot with rational functions and equations, which is that whenever we can factor things, we do so. This is already fully factored, but in the denominator, I can factor x squared minus 25. This is the difference of two squares. Factors into x minus 5 times x plus 5. And I can factor x squared plus 6x plus 8. This is x plus 2 times x plus 4. Hopefully we're feeling very comfortable in our ability to factor. Otherwise, we might want to ask our teacher for some help on redressing that issue, or rationals will not go well. It's an essential skill. Okay, so let's look at this. These are multiplying together. And so I'm going to rewrite this whole thing with the denominator factored. I didn't change the numerator. We've got x plus 4 times x minus 5 divided by, this became x minus 5 times x plus 5, and this became x plus 2 times x plus 4. These are the factored forms, and the reason we want to factor is because when we're dividing, multiplying and dividing are inverse operations. You will notice that x plus 4 is being multiplied by x minus 5 and divided by x minus 5. We can kind of cancel it out, and I'll explain why it's not exact in a second. And we can think of this as 1 times x plus 4. Even though there wasn't anything multiplying here, we can always think of it as being multiplied by 1. And we'll notice that 1 is getting multiplied by x plus 4 and divided by x plus 4. And so those factors will cancel out, mostly. And what we end up with left on is there was nothing left on top, but there was 1 multiplying times this. And so we can always put 1 divided by. So we've got 1 divided by. What's left over in the denominator is x plus 5 times x plus 2. Now, I said these mostly canceled out. It turns out that for these to be equal, we need to state what values we weren't allowed to have in the original one, there are two excluded values that we canceled out. And I'm going to say x cannot equal 5 or -4. And there are a couple different ways to write this. X cannot equal 5 because before we had times x minus 5 divided by x minus 5. And if x were to be 5, we would get times 0 divided by 0. And we are never allowed to divide by 0. This is called an excluded value. And when we cancel it out, we need to make sure that the excluded value still needs to remain. It looks, for all intents and purposes, in this one, that we could plug in 5 and get 1 divided by 70 or something like that. But when x is 5, for it to actually be equal to the one above, we need to say that x cannot equal 5 because it needs to be an excluded value. That's where this -4 came from also. When x is -4, -4 plus 4 is 0, and we don't want to be dividing by 0 in this original one, and so for these to be equal, it still needs to not be dividing by 0. This will come into play more with graphing, which we'll see in our next example.